Hi, in this video tutorial, I'll talk about the spring, basically the model of the spring and how the restoring force is derived, and the idea here will be able to extend it to the dashboard. So I'll just talk about the spring here. So here's the spring here, and whose both ends are free to go. And first of all, number one thing is the x1 and x2. Okay, these two are defined, as we were saying, they are defined with respect to the equilibrium position, and as we were saying, the equilibrium position essentially is just the position when the spring is at rest. Okay, so the equilibrium position, that's number one thing. So in the class we were saying, we give the formula, we're saying, okay, so if we have a mass attached on the right side, okay, then the free body diagram for this mass, if there's no other external force, only the restoring force of the spring, then the restoring force of the spring is k x1 minus x2, which is to the opposite of the direction of the motion. Okay. So in this here, the primary motion of this mass on the right side is x1, and this primary motion will cause extension of the spring. Okay, so when you cause extension of the spring will try to drag you back. Of course, the direction of the restoring force is in the opposite direction of this x1. So the primary motion is x1, and so the x1 minus x2, which is the compression for that, so that's the restoring force. So that's the formula, right? And if the spring, if there's a mass connected on the other side of the spring on the left side, then the restoring force is F equals to negative k x2 minus x1. The negative sign here means the restoring force is in the opposite direction of the motion. Now the direction of the motion in here is x2, so that's why the free body diagram shows the restoring force is in the opposite direction of this x2. Okay, so that's the formula we're giving in the class. And I just want to mention another thing is regarding the direction of x1 and x2 that we labeled it here. Okay, so the x1 x2 direction, the direction here basically what we call this is the reference positive direction. Okay. So reference positive, this is basically just like the idea that you have a coordinate system, xy coordinates, for example, right? So you label the positive direction, okay, for the xy coordinates, and that's the positive reference direction. Now, what the actual direction motion, of course, is probably in the opposite direction. So that's the idea here. Just that's the opposite, the reference direction. Okay, so let's take a look at this one here. So this diagram I didn't show in the class. So let's see if I have a spring here. Okay, and I define these two locations here as the equilibrium position for the left and for the right side. Okay, this is right. And again, equilibrium position is the position when the spring is at rest. So let's say for some reason, okay, then the spring on this left side was moved by x2, okay, and at the same time on the other side is moved by x1, right? So that's what happens here, and it's very easy to compute the net change of the length of the spring. So if this is your original length of the springs, which is x0, and under this kind of a movement, then your net length, okay, so the new length, or the new length of the spring becomes L0 minus x2 minus x1. Okay. Or if you take the negative sign out, then the new length, okay, is becoming L0 plus L1 minus x2, which is the same thing. Okay, so that's basically the new length of the spring. Then you probably ask, what about the net change of the length of the spring? Okay, so I'm going to use a real number here to illustrate the idea here. Okay, so let's assume I have a motion which has x2, let's say, equals to 1 meter. and then x1 equals to 0.5 meter. Okay, so that's one change at here. Okay, x2 to 1 meter, x1. So then what happens here is the spring, okay, under this motion, the spring length, okay, then becomes L naught, okay, minus x2 minus x1 equal to L naught minus 0.5 meter. Okay, so the length becomes this, and apparently this length is less than the original length L naught. So what does that mean is the spring is under compression. Right, the spring is under compression for this much of a movement. Okay, so if a spring is under compression, okay, use our basic knowledge apparently, and the spring will try to exert, okay, will try to exert force, okay, outward. Basically, if you push your hands, okay, press the spring, use both of your hands, right? You experience exerting force from the spring to your hands, so exerting force to outward. Okay, so then if I have a mass, okay, connected with the spring, okay, a mass connected to the spring, okay, then on the left side, okay, then because the spring is under compression, and the mass, okay, will experience a force in this direction, even though that your motion of your mass is x2, right? So you're really experiencing a outward force at here, which is k 0.5, this much of a magnitude. Okay, and according to our calculation, of course, if you have a spring and connected, you have a mass connected on the right side, okay, then because of the compression, okay, the spring will experience a force in this direction with a magnitude of 0.5 k. Okay, so this is x1 here for this ones here. So that's from the actual number. That's what we get about this. So let's see. Okay, this number is how about our formula, right? Is our formula comply? Does our formula comply with our actual numbers here? So what we see, our formula says, okay, is this is a k x2 minus x1. Okay, and our formula for spring connected to this side here, okay, is k, basically is k x1 minus x2, right? So that's the formula. Okay, so let's see if I plug in my actual numbers x2, x1 here. Okay, so this side becomes 1 minus 0.5 equals 0.5 k. Well, that matches exactly what we have here, right? That match exactly what we have here. Okay, so that's good. So this side is good. So we trust our formula. So how about this? The other side here. Okay, for the other side here. So this guy here equal to k 0.5 minus 1, okay, which is negative 0.5 k. Well, negative 0, what does that mean is, even though you're in this case, even though you're drawing, okay, the restoring force is drawn in this direction. So your actual calculation here is negative 0.5 k. So which means the really the restoring force or the external force on this mass here is moving in this direction here with a value of 0.5 k. Right? So that's what it really means for this step here. Now, does that is that if you look back, okay, if you look at the back over here, okay, and that match up with our explanation without even use the formula. Okay, so that basically tells you our formula is definitely right. Okay, and the physical meaning in here, of course, it can be explained using some real number. The direction of the force really depends on the value of the displacement of both sides of the spring. Okay, so in actual modeling, okay, just bear in mind, okay, which mass you're analyzing. Okay, and So maybe I'll give you an example here, another example of a modeling example here. Okay, so let's just see I have a mass over here. Let's see, now this time I'll put this mass, okay, in a horizontal position. Okay, yeah. Okay, so let's say this mass has two springs connected on both sides. Okay, and now I say, oh, I define the mass movement. Okay, I'll define the mass reference positive direction for this mass is this direction here. Okay, so what is the equation for motion for this guy here? Now apparently, and I'm gonna just derive a free body diagram for this mass here. Okay, and for if I look at this side for K2, okay, the compression for K2 cause a restoring force in this direction, so K2x. And if I look at the mass K1, the direction of motion of the mass cause extension for K1 actually, so then restoring force is still in this direction. Okay, and there's no other external force, then the Newton's second law says the mass multiplied by acceleration equals to the total net force. Now, because right now your positive direction of the motion is in this direction here, so your restoring force in the opposite direction of the net of the reference positive direction. So that's why I put a negative K1x minus negative K2x at here. Okay, so then that equals to negative K1 plus K2, okay, and multiplied by x. So that's your equation for motion for this simple system. Okay, thank you.